Thank you, Lauren. So welcome to our last day of class at the UMass Clean Energy Corps for 2022. So this is a project that started with a discussion with MA and Denise about possibilities for some. They have some very ambitious ideas about what to do with really the entire town property of in Deerfield. And so we went on a visit. We explored these two buildings. We thought about exploring additional buildings. We explored the elementary school that's kind of across the way and saw that in many ways it's in really good shape and not very ripe for connecting to a district energy system with the other systems, at least not at this point. So earlier in the semester, we kind of shared some ideas about the elementary school, and that's not going to be the subject of this presentation. This presentation is really going to focus on the church, basically the two historic preservation cases. And so I will just hand it over to the team. Let me, I guess I'll hand it over to the team because some of them are on Zoom right now. So Olivia.
Yes, hi everyone.
And Megan Iskowitz is about to graduate with her MArch, and Olivia is about to graduate with her BS in building and construction technology. And then in the room we have Mike and Brandon, also about to go off into the world of not being in college. So with that, I'm going to share my screen and hand it over to the team. Okay.
Alrighty. Hi everyone, I'm Olivia. I think Ben already introduced us. So he also already gave you the background that our team a couple of months back went to go visit a few town buildings. We found that after speaking with MA, Denise, and Carolyn and hearing about some shared community values, we compiled Deerfield's list of ambitious goals that are on the screen here. We've put together our best efforts and suggestions for the town of Deerfield throughout this presentation, and we intend to address each and every one of these goals throughout. Alrighty, so we have seen the condition of these buildings and analyzed them. We find that it is now up to you folks to decide whether you are willing to put in some major investments for improvements to preserve the historic significance of these buildings, or if you would rather demolish them. If you do decide to go the route of preserving these buildings, our proposal illustrates how you can get some net zero carbon buildings. These suggestions are not minor alterations. These are big developments, and you cannot half measure these improvements. Our proposal to you is not cheap and not an easy fix. We will need you to truly reimagine these buildings as the high performing zero carbon buildings they can potentially be. Okay, so with considerable investment, you can update the usage and programming for the former grammar school, known most recently as the Senior Center, into future town offices. And the church can be used as an auditorium and senior center. These buildings have potential to become high performing and zero carbon. It is critical to address the water management, and we have specific recommendations for that. Also, methods that link the heating and cooling for both buildings from a connected ground source system, and techniques for passive cooling designs. Here's a visual of our proposed system overview that we will circle back to throughout the presentation and later again. This is our agenda for today. We plan to address specific elements about the recent senior center and church. Then we'll discuss water management and shared geothermal systems for heating and cooling, and go over the HVAC systems before we tie everything together for you at the end. I'm gonna pass it over to Brandon now to talk about the senior center.
All right, hello everyone, I'm Brandon. So So when we visited the senior center, we saw the conditions of the brick and saw some serious structural issues that we could not fix solely with cosmetic and surface repairs. The brick cannot be left exposed, and as you can see in the pictures, the mortar is eroding and the exterior brick is breaking. The bricks are already spalling, which can lead to large chunks of brick falling from the structure. Swelling starts off with small cracks, but it can grow bigger until the entire surface deteriorates. Most of the horizontal surfaces are without a drip edge or kerf, and the roof concentrates outfall in critical corners with splashback damage. This is not good structure for keeping water off the brick. These diagrams are temperature profiles showing 3 different scenarios for brick. In each of these diagrams, you see a black line and a blue line. The blue line is showing the temperature at which water freezes, and the black line is showing the temperature gradient from cold outside to room temperature inside. The first is the current condition showing how there is no insulation. So as you can see, with no insulation in place, during the winter, the 2 exterior bricks are at risk of spalling due to the low temperatures, excuse me, due to the low temperatures at which water would freeze in the bricks. The next diagram would happen if you installed interior insulation. Interior insulation will make it so all the bricks are at risk of freezing, because if the interior got insulated, none of the bricks would be heated from the inside. We propose that you use exterior insulation. As the last diagram shows, exterior insulation prevents bricks from freezing at all. And as you can see from this, we obviously know you don't want to have exterior insulation for everyone to see. So we propose that you use exterior insulation siding on the side facing away from the street. And where it does face the street, we propose the use of exterior glazing to protect the brick from external wetting. And now that it is protected, you can insulate it from the inside without worrying about bricks freezing. And now I will hand it off to Megan.
Thank you. Hi, everyone. My name is Megan. Like Ben said, I'm actually about to graduate in a week with my Master of Architecture, and I also did my undergrad in architecture with a minor in building construction technology. So moving forward to the building, the current proposed design does not address the damage and future functioning of the current brick structure, and the building facade condition would continue in the trajectory that it is currently on, which Brandon has previously explained to us. An auditorium addition is not necessarily needed. This need for a gathering space can be satisfied through the existing property next door. Lastly, brick on brick won't necessarily match if that's the intention. It will simply just draw more attention to the difference in materiality appearance. This will not mitigate the fact that it's a new structure combined with an old structure. This is an example of a massing floor plan to express what type of additional space may actually be needed. By removing the auditorium, the only addition that's truly needed is an updated method of accessible circulation. This would house an elevator as well. In addition, this could be an informal meeting space with opportunity for tables and casual sitting areas. The inside of the existing portion of the building can serve as office spaces that this building needs to house. When addressing the current issues with the brick that Brandon has introduced, we came up with 2 solutions. The first solution addresses the historic and social value that the brick building holds, encasing the exterior in glass curtain walls. On the back side, facing the parking lot and not the street, we've added an exterior cladding system. This would provide insulation and protect the integrity of the brick. The interventions we proposed to make were the least invasive method to preserve the existing structure. There were challenges with accessible entrances, so moving the main staircase to the back with the elevator resolves this. As previously stated, the circulation space can also have other informal social uses as well. South College on UMass Amherst campus is an example of integrating an old brick building with a new addition. This shows how this can become a design opportunity for the interior quality of the user through materiality and the level of light added into the space from the connection points of the new and old roof through an atrium that's been created. So moving forward to some exterior cladding precedents. These precedents offer an example of what mixing a modern cladding addition with a historical building could look like in a real life project. With South College on the bottom, showing a variation in new and old materials, the gray responds appropriately to the aged brick. South College is a local example at UMass Amherst campus of how to respond to a traditional brick building. Hedberg Cultural Building on the top is an example that shows the diversity and variety available in cladding systems and their ability to respond to historic structures. Next, I just want to talk a little bit about terracotta cladding as an option. Terracotta cladding is a highly durable material. It's weather resistant, has a Class A fireproof rating, it's UV resistant, it requires low maintenance, and it has low embodied energy. This is very sustainable and easily recyclable. Once you have a rain screen, like the diagram expresses on the bottom, it's very easy to pop them in and out and change them for maintenance purposes or even potential design reasons. This is just an example of what a colored cladding system could look like on the building. And then moving further into the building technology side of things, the glass casing in this building can be referred to as a tram wall. This is a solar collector, and the thermal mass of this mass wall is a storage medium for the heat that is collected by the sun. And by managing the glazing, as well as internal and external venting, we can make sure that we are always distributing heat to where it's needed. In our case, the building faces southeast and southwest, not due south. Because of this, solar gain can increase in the winter due to winter sun, which could then have the potential to cause overheating. We needed to figure out a way to manage the solar gain appropriately through the use of an automated motorized vented facade that opens itself up when it overheats. In the summer at night, the glazing will open to mitigate solar gain from daytime to cool off with the nighttime air. The mass wall will then be regulated in temperature to protect the inside from experiencing change at all. This would all be controlled through automated specified temperatures, as well as times in sync with the motorized ventilation. So the SDU Colding campus has a climate controlled automated facade. This dynamic solar shading adjusts to the specific climate conditions and user patterns, which will then provide optimal daylight and a comfortable indoor climate along the facade. The solar shading system is fitted with sensors, which continually measure light and heat levels and regulate the shutters mechanically by the means of a small motor. This is the same principle that can be utilized in a way to address the necessary release of heat in the tram wall we have proposed, opening and closing windows based off of temperature parameters. And then lastly, we have a local example of this method being implemented, which is the Integrated Learning Center, or the ILC, on UMass Amherst campus. As you can see, the exterior windows pictured are self-ventilating. And then we'll return to more details about these systems after we speak about the church.
Hello, everyone. Thank you again for joining us today. My name is Mike. I'm going to be starting off with the church. There are existing plans to use as a temporary holdover for the senior center until a new structure is built. But as far as we can find, there isn't a well-defined programming use planned after that. Being that it is in a central location and sandwiched between the current town offices and the current unused senior center, the location is excellent. It can serve a multitude of purposes and has the potential to be a very high-performance building. Additionally, there is a published survey on the town's website that illustrates that the community wants this building to be used. So the community goodwill for restoration is already there. As is written here, there's 4 basic steps to fix the church. It's number 1 is to correct the structural deficits of cables and turnbuckles. Number 2 is to mitigate the water problems. Number 3 is insulating the envelope properly. And number 4 is installing the new HVAC system. This here's a picture from the attic, and as you can see, the main retention beam has been warped enough that it's not sitting where it should anymore. Again, a structural engineer would be able to correct this. You can see that the insulation isn't nearly as robust as it could be and largely isn't doing much. Also, it isn't very visible in this picture, but you can look down in the wall cavity where the rafters sit and see that the walls are completely empty. And there is also a shaft from the attic that leads down to the basement. So thermally, the whole building is interconnected, which can be corrected with a few steps. And here are those steps. This is a very simple visual of the attic with the steps listed to correct it. Basically, installing joists and plywood will stiffen the structure, provide an area to run HVAC ducting underneath, and a plane for the insulation to rest on. Essentially, the whole point is to exclude the attic from the unconditioned thermal envelope, because sending heating and cooling into the attic is a waste of energy and a waste of money. And with this, you have a very unique opportunity here in that the existing wall cavity is around 8 inches deep, as opposed to the normal 3.5 or 5.5. So it's simple and relatively inexpensive to turn this wall into a very high performing one just by using blown in insulation. I do have a slide later that will show finished R values. What needs to be done first, though, is a deeper investigation of what is currently in the walls. There are 4 likely possibilities. One, there's a vapor permeable, weather resistant barrier over board sheathing, in which case you're good to go with no other steps. Number 2, there's a vapor permeable WRB over old siding, in which case you should also be all set. Number 3, which is the most likely, is that there's fan fold foam. And unless all the seams are sealed and in good condition, that will need replacement. And 4, if there's a vapor impermeable backing, it has to be totally replaced first. However, if you're faced with number 3 or 4, it does present you the opportunity to use more sustainable and resilient and historically appropriate materials for replacement. So for the basement, it has 3 big issues. It has extreme water infiltration to the point where you can see a riverbed has been carved out onto the floor. The ground heat loss is pretty substantial because the foundation is not properly sealed up. And 3, capillarity needs to be addressed. So for capillarity, because the insulation of the church is pretty much non-existent, every time the wood sill gets wet, it has an opportunity to dry because of how much airflow is moving around. And if the building gets sealed up properly, that won't happen anymore. I can't stress how critical this one detail is, so I just want to make sure I highlighted it for you. As far as insulating the walls, it's a pretty straightforward process that's laid out here in writing. And the drain installed on the inside will reroute the water that does get in, and I'll be covering that in a few more slides. So here are a few more tangible numbers for you. The numbers on the left are the current IECC R value code minimums for our climate zone, and the measures I've laid out for you give you the numbers on the right. As you can see, the walls, the ceiling, and the basement all exceed code. And the windows in the church are functional, but not fantastic in an energy sense. So in case window replacement was something you would consider, especially if the siding needs to be replaced, I've also included the potential U values that would provide. All right, for drainage, it's a pretty basic solution. This is a very, very simple representation, but basically the red line is an external drainage trench, which needs to be external to avoid capillary action on the bricks. The blue line is an internal drainage trench because digging around the exterior of the building can compromise the foundation. The green box is a combined drainage field, which can be installed and then paved over for parking if you want to. And the orange line goes to a cistern for overflow just in case it's necessary. And this is a quick representation of the typical drainage field where the parking lot basically gets excavated, lined with fabric, and refilled with gravel. And the purpose of the system is to capture runoff and displace water from the roofs and give it a place to drain slowly over time so it can prevent flooding inside of the buildings. And as I said on the last slide, this type of system can be paved over so it doesn't take up any unnecessary space. And again, this is just a typical example of a cistern to contain overflow, which can be sized as necessary. And the nice thing about this kind of 2 drainage system is that a cistern can be used to do other things than just contain water. It can also be used as free water for landscaping or irrigation. And as far as the HVAC system goes, because these 2 buildings are next to each other, they can very easily share a system instead of having 2 separate systems, which will increase the costs. This shared system is complementary, meaning that each building can pick up deficits in the other if need be. And because of the required excavation for the water mitigation, there is a unique opportunity to use geo-exchange loops without any extra excavation, which Olivia is about to go into more detail about.
Yep. Alrighty, hi again. So I'm gonna go over some different types of geothermal heat pumps and systems to consider for using for these two buildings. First, we have closed loop systems on our left, which split up into vertical and horizontal exchangers, also known as boreholes and slinky loops. There's the big cost distinguishment between these two that come from boreholes' expensive deep drilling costs. Boreholes do take up less horizontal space. I say this can be an ignorable benefit in our case because we have so much opportunity to take advantage of the plain area that would already be dug up if we consider the parking lot space that Mike mentioned, but I'll come back to this in a bit. There's also the possibility for slinky loops to lose efficiency over time from lack of balance. Due to this system being closer to the ground level, it is more susceptible to outside temperatures than a deeper in-ground system would be. Then there's the open loop system on the right. That works by extracting groundwater and dumping it back into the ground. However, we don't know about the groundwater resource situation, so it makes more sense not to overcomplicate things for our geological space. Okay, in this graph, the yellow line corresponds to slinky loops that are shallower in the ground that accommodate for earlier on in a heating or cooling season. And the darker green line corresponds with slinky loops that are placed deeper in the ground, accommodating for later in the seasons. Basically, if slinky loops are placed at different ground levels, this will provide balance throughout each season, creating a year-round balance. We propose you go for the more cost-effective option. We intend for our suggested building designs to create self-sufficient heating and cooling within themselves, allowing the slinky loops to restore and recharge on the daily and prolonging its functionality throughout these different seasons. If you invest in the slinky loops now, you are not limited to future additions, meaning if you find that more support is required, there's always the option to add some boreholes down the line to improve the heating and cooling balance. To the right is our conceptual design of a hybrid method of systems that includes both the vertical and horizontal techniques. This shows how multiple geothermal systems can work together. If you'd like to take a look at that. If the slinky loop's temperatures are somehow unbalanced, the ground pump will receive a signal, which will close the valve to the slinky loops and reroute the heating source to the borehole system and vice versa, creating this on-off switch effect between the two systems that operate in both directions. Okay, and just to reiterate the immediate convenience of the slinky loops for you folks, where Mike mentioned underneath the parking lot for a drainage catchment, this would be a great opportunity to throw in some slinky loops. Really, any plain area that is planned to be excavated is a great opportunity to incorporate slinky loops for geothermal heating. Okay, I'm going to pass it back to Brandon now to share some HVAC concepts with you.
All right. Hello again, everyone. For the church's HVAC system, we had to deal with specific challenges such as rapid change from low to high occupancy, rapid change from heating dominated to cooling dominated, high ceilings, and aesthetic concerns. The solutions we came up with to deal with these challenges were displacement ventilation, a dedicated outdoor air system, and radiant heating and cooling. Displacement ventilation, it has a higher supply air temperature, which allows economizer cooling to increase. It allows heat recovery and improves occupant comfort by not overcooling. Displacement ventilation has low velocity, which reduces fan energy. It utilizes natural buoyancy of contaminated heat plumes, which will be shown in the next few slides. It is also compatible with low temperature change, radiant heating and cooling. Heat naturally rises, and with displacement ventilation in place, you have something at ceiling level to take it away. Removing using heat rising from its natural buoyancy, displacement ventilation provides a 17% reduction in fresh air supply, which also translates to 17% reduction in energy use. This picture shows a simulation of how displacement is better than mixing. Carbon dioxide is a good indicator for airborne pollutants such as viruses and bacteria. And this picture shows that when you mix the air, you are also mixing everything else too. Displacement makes it so any polluted air rises more quickly out of the breathing zone. We propose to use a dedicated outdoor air system with energy recovery and wraparound heat pipe that delivers room temperature air. The heat pipe starts by letting outdoor air enter the unit. Then the energy recovery wheel cools and dehumidifies the outdoor air by recovering energy from the exhaust system. Then the first section of the heat pipe pre-cools the air next to the cooling coil, further cools the air to gets rid of moisture. Then the second section of the heat pipe reheats the air to about 70 degrees, which is the supply air. For radiant heating and cooling, hydronic radiant panels can be sized to provide 100% heating with low water temperatures. It can also provide 100% sensible cooling which can remove heat without changing the moisture content. Chilled water is used for both processes and allows the use of relatively warm waters for cooling. Latent cooling or humidity must be handled by the dedicated outdoor air system. This image is a conceptual schematic of a cascading chilled water loop. The way this works is that water enters the dedicated outdoor air system's cooling coil at 44 degrees and leaves at 54 degrees. Then a three-way mixing valve mixes the return chilled water to supply radiant panels with 57-degree water so that the average water temperature is 62 degrees, which is well above dew point, and the final return temperature is 67 degrees. The result of this process is 10% improvement in chiller efficiency and 63% reduction in pump energy compared to typical return water temperature of 54 degrees. For the new town office's HVAC system, we faced one challenge with the proposed exterior glazing or trauma. The problem is that there would be a thermal lag of 12 hours, which means heat delivery occurs during unoccupied hours. There is also overheating on glazed sections in heating and cooling modes. We came up with both passive and active solutions. The passive solutions Megan explained earlier, but just to recap, they were to have operable windows and transfer fans and ducts to harvest daytime heat, also to use economizer cooling when available, and to use night flush cooling of the brick, thermal mass mainly in the summer. The active solutions are heat trading and heat storage. Heat trading is done with a 4-pipe hydronic system to enable simultaneous heating on opposite sides of the building, and also provides it to the church. Heating storage rejects heat to the ground to provide annual balance of the geo-exchange system. This is the new town office schematic, HVAC schematic, which is showing how each room will have its own system to control the desired temperature. The trauma is being depicted on the left side of the picture, and the trauma overheats the room, so the fan coil unit is in cooling mode. The heat that the fan coil unit takes out of the room goes to the water source heat pump, and therefore is directly sent over to the other room where heat may be required. On the right side of the room, the energy recovery ventilator, or ERV, separately provides fresh air to all the rooms at roughly room temperature. So how would this heat trading work? Well, you use 2 separate tanks, a chilled and a heated buffer tank, for a heat recovery system that will be used to satisfy simultaneous loads. This is the most common operating mode for the office during all but the coldest periods, and will represent about 1/3 of the heating for the church by supplying excess heat from the offices directly to the church. This chart shows that the energy use of the offices and the church are designed but operating separately. They both don't use that much energy. Heating is almost eliminated for the office, but is the dominant demand for the church. Total cooling is much larger than heating, which is not a problem for the ground source heat pump. Cooling for the office is much higher, and that's because of the glazed facade that acts as a solar thermal collector, as you can see here. Now I'll hand it off to Olivia.
So, all right, here's an imbalance, and this is a problem. You don't want to deposit excess heat into the ground and jeopardize your cooling efficiency. To the right is an example from a building in Korea with a similar, slightly warmer climate than ours, and they have a temperature imbalance that is declining their cooling efficiency over time. As you can see, the numbers going up. To avoid running into the same problem, you will need a solution that avoids depositing heat into the ground and instead removes this excess differently, so that there's balance. Balance is the goal here.
Okay, so the trommel causes the problem acting as a solar thermal collector, but as long as we can open and close and actively manage the trommel, we can use it for cooling. We can open and close openings in the glazed facade to use outdoor air to cool or pre-cool the thermal mass of the building or off the trom wall by using economizer cooling and night flush cooling.
So this slide is a representation of heat transfer from both buildings. And as you can see, the heating and the cooling, which are the red and blue, are closely matched when the passive system is set up properly. And each building can operate in a complementary way where heating and cooling demand from one is satisfied by the other. The hash bars at the bottom represent heat being removed by economizer heating, and the solid bars represent electrical use. I want to draw your attention to the 5 that is circled on the left side, so you can just get a scale or a sense of scale for the next slide. These slides represent electricity for heat transfers, where each color above the orange lines is directly interacting with the geoexchanger. Again, the circled 5 just shows how much the demand has been reduced, and that's because the system has such a high efficiency. The shared system will demand around a 30 megawatt usage annually, whereas having 2 independent systems would demand around 51 megawatt hours annually. This is just a simple graph showing how well balanced the heat extraction and rejection is with this system. The balance is vital to avoid overheating the ground over time, which would in turn reduce the efficiency of the system overall. So just to summarize, we've designed this proposal to optimize the potential use for both buildings. It'll require some major structural and shell renovations to avoid the current problems like capillarity and water infiltration, and additionally address the structural defects in the church. But with these measures, however, the insulating, displacement ventilation, the 4-pipe system, the shared geo and heat pumps, these 2 buildings have the potential to be extremely high performance, and they can continue to serve the community in the way they should. It's just another overview of the plan. And now it's up to all of you if this is the path you want to take in preserving these buildings. And if so, I just wanted to very quickly outline the next steps. First, you would need to consult with a structural engineer for the church and get pricing, and likewise a civil engineer for a detailed drainage plan. You could hire an architect to draw a remodel for both buildings, and then get a mechanical engineering firm who has a proven track record with geothermal pumps to design the system. And finally, if you decide to go forward on this proposal, the UMass Energy Extension faculty is available at any point to act as an advocate. And that'll wrap the presentation up, and I want to thank you for being here today and open it up to any questions.
So I guess what I'll do is stop the share and see if anyone has any thoughts or questions that we can answer or things that we missed. Yes, so Julie has the handout.
I guess I was first on the button or something. This is a great presentation. Thank you very much. It's very interesting and makes me want to ask a million questions. Did you look at reliability of the equipment that you're putting in with regards to long-term operation of these systems?
What I could say is that in all of these cases, they are well-established technologies.
Mhm.
So ground source heat pumps and water source heat pumps have been around for a very long time. They have been improving dramatically over the past decade. But there are many, many cases of ground source heat pumps that were installed in the 1960s that are still operating. So essentially the ground loop, which is kind of the big expense that's difficult to change, that is pretty permanent. You see essentially the same slinky loop technology. A lot of people started installing these in the 1960s and 70s, and those same heat exchangers are running.
Yeah.
Now, with
I would
anything motorized, like those window operators, motors tend to be placed, on the decadal level. All the other equipment, fan coil units, for example, that are the DOAS, all of those types of equipment, those typically are expected to have, say, a 20-year equipment life cycle. The simpler fan coil units that we're specifying for the offices, you would expect to last much, much longer than that, just because they're very simple machines.
How about the controls? Go ahead.
Sorry, just to touch up on the ground loop systems. So the slinky loops are a great solution for right now in the immediate. Like I said before, you can always add boreholes down the line, and that doesn't mean that the slinky loops won't work. It just means that they might need a little bit more support, but they'll still be functional, and it's a great long-term investment to immediately lay down throughout the parking lot.
How about the control system?
Control systems are always updating. So the control systems that I learned how to use are still functional, but if I have my choice, I'll put something else more automated on top of them. Now, we already have a high level of automation available. The key would be, and any engineer who designed such a system for you would make one that is basically BACnet compatible, which means that as long as the sensors are in place, and you might have to replace a sensor here and there in all of these systems, but as long as you have a sensor in place, you have a consistent communications platform. And so whatever technology is laid on top of it will be able to control the systems. But yeah, control systems change as technology improves.
Yeah, they update.
Yep.
MA? Oh, you're muted.
Muted.
There we go.
There you go.
Sorry, it's a perennial problem for me. Couple of questions. One is, as you might have noticed, maintenance in the town of Deerfield has been somewhat lacking. You've wandered through some buildings. We don't have experts. We may never have experts. And do you recommend like having a maintenance, a contract, some sort of contract for maintaining this more complicated system of, how do you go about compensating for the fact that it's not likely to be maintained well or knowledgeably?
So the key to any of these newer systems, right? And we're taking a bunch of long established components and assembling them in a way that is not unknown, but is not necessarily commonly understood by every single one of the trades that's operating around here. So the key to any modern building, and I think Megan could back me up on this, is that when you deliver a building, you actually need to deliver an owner's manual. And you get that with a car, right? So you need that particularly with a new building. The nice thing is all of these components are very replaceable. So mostly we're talking about circulator pumps. I can go down to Northampton Plumbing Supply and pick up any of the pumps that we would specify. So if one goes out, it's pretty easy to replace them. The control systems, again, as long as they're, say, BACnet compatible, one BACnet compatible controller goes with another one, they're all replaceable, and any HVAC technician would know how to control that component. Same with the heat pumps. They are self-contained units. You may have to, hire someone to do work on that particular, probably warranted piece of equipment, just like any other piece of equipment. But unlike, say, refrigerant systems where you have, the air source heat pumps that you're used to, say, in your house, there's a refrigerant line connecting the indoor unit and the outdoor unit. And that's often, those connections are often where you have failures because those are done in the field. Here, the only connections are water connections. And that's basically traditional plumbing. If it leaks, you need to fix it. But that's the essence of this system, is actually the simplicity of it.
Second question? Thank you. And this presentation was great. I think I'll have to watch it 3 more times in order to get all the meat out of it, but I follow the generalness of it. Is this system expandable as we maybe add new buildings or increase the campus in situation if we decide to?
Yes. Short answer is yes.
Yeah.
And in fact, the more you expand it, the better it gets.
Yeah.
So you notice the big challenge for us was Megan designed us a big greenhouse to put half the building in. And so the big challenge was, how do we get rid of all that heat without creating an imbalance in the system? Well, that becomes less and less of a problem and more of a benefit if you have a building nearby that has high heating demand, because now you're extracting more heat from that same slinky loop. So the more balance you have, the more we can add heating to this system, because we basically put a giant solar collector on your school, your former school, the old grammar school.
Yeah.
The better the system functions.
Excellent. Thank you.
And
Julie.
a follow on to MA's question. So if we were to, for example, tie the library into this, and the library has an existing heating system, can you talk about retrofitting geothermal to an existing heating system? And I'm realizing as I'm asking this, I don't even know what they use. Do they have radiators in there? I think.
Carolyn, do you know or maybe Carolyn's not here anymore.
Yeah, no, I am. I don't know offhand what they're using,
Yeah.
but it will be replaced. It will be replaced in part of the renovation, Julie. Anyway,
The whole
Those-
system. The whole system will be replaced. Yeah, it's a very inefficient system. I know that, and I think it's a boiler.
yes, it is. Pretty sure, but it will be replaced anyway.
So libraries, like auditoriums, are complex. They have interesting hours. They have very, very strict, very often if they've got books that you need to create a condition for the books that doesn't let them deteriorate. So without knowing this particular building and its new design really well, I'm not going to be able to say, well, here's the system you need to install. But what I can say is that just like the auditorium function that we proposed for the church, you're going to need humidity control, heating, and cooling. And just as the church is able to use hot and cold water to do that, the library would be as well, although the specific equipment that's using that water might be different.
Let me ask a slightly different question. If you have a building that has existing forced hot air, that is like a boiler system and you shift over to geothermal, is the ducting that's associated with a boiler system likely to be sufficiently sized for a geothermal, which typically operates at a lower temperature?
You're asking the right question. And the answer really has to do with what air handling you have available and what the condition of the ducts are. If so, it's really a question. It's this, again, it goes to the specifics on those ducts. You can have, if you already have a boiler, that means you have a water coil that's in the airstream. This would just really essentially require you to have a bigger water coil in the airstream. So more surface area, same amount of air, and you can transmit the same amount of heat.
So the air temp would stay the same. It would just require more.
Yeah.
Okay, got it. That makes sense. And then a third question, I'm thinking about our campus, the way it's set up, and then the elementary school and the high school. There's a stream between this campus and the elementary school and the high school. And in my 3-second thought about it, it would be really hard to get the geothermal across that stream. It doesn't make sense to me to tie those two buildings into this. Do you agree with that, or am I off base?
I do agree with that, partly because excavation costs get to be large, and because the school has its own operating characteristics that may be a challenge to match with the other buildings. But it's also, and you would need more heat exchange space. You just simply need the borehole field that Olivia was talking about, without any question.
Yeah, Ben, do you think that the open loop system could be useful for that sort of situation if it's already near a stream?
Probably not, because of permitting and
Environmental.
all sorts of regulatory problems with that. We did not explore the aquifer well enough to be able to say a pump and dump system would work in that location. Doesn't mean it wouldn't. There are problems with moving free water, and that often result in maintenance issues, and that's why it's a system that makes sense and yet has difficulties. And so I tend to stay away from it where I can, basically because it imposes a large maintenance burden on it. But yes, in short, the school in particular has very good equipment already in place. At least the school that we went to, that elementary school.
Yes, correct.
Very good equipment already in place. And it makes sense to develop a glide path for that school so that you can wean yourself off of natural gas over time as funding becomes available, as technologies improve. It may make more sense to use an air-to-water heat pump for that school, just based on when it's doing what it's doing and how that technology has been improved. That's why we left it out of our presentation.
And the more I think about it, the more maintenance that sort of a system will need and require.
It's hard to say.
Sorry?
It's hard to say, isn't it? Because you need to specify the entire system to figure out what are the components.
Okay.
Great.
Hi, I am wondering how historic buildings like this that do not have, in essence, a greenhouse envelope and the trom wall concept, how they are able to insulate their buildings and make them, you know, relatively efficient, if not as efficient as the trom wall would make this. Because my gut feeling is that people will be very resistant to making such a dramatic change to the, to the character of the building. I find it very interesting and exciting, but I'm just curious what the other options might be.
So I would say that in my experience, been doing this for a while. In my experience, 90% of the brick structural masonry buildings that I encounter can be insulated from the inside. And the reason for that is because they have, and they can be heavily insulated from the inside. It doesn't matter if the brick gets cold, if it doesn't get wet and stay wet. And so for 90% of these buildings, it's easy to keep water off the bricks so that it's either the quality of the brick is high, in this case it's not, and the details on all of the horizontal surfaces shed water away from the building. Finally, you can, at the lower levels, you can add a sacrificial layer of a plaster, basically, of pargent that periodically will need to be replaced because you're actually asking it to do the spalling for you. And so it's a sacrificial layer that it's a very traditional approach. I would not want, let's just say, I would not want my name associated with an attempt to insulate this building from the interior because of the quality of the brick and the horizontal structures that direct water into the brick. And because of just by looking at how it's performing right now without interior insulation, this is not a building that I would want to insulate from the interior. Many, many, many other brick buildings can be insulated to very, very high levels and be just fine. I just think this isn't one of them. Any other, I realize that's not an answer anyone wants, and it's not the answer we were coming to look at. And that's why Olivia kind of prefaced this by kind of trying to make it clear this is a big decision point, because at least in our assessment, you either make a big move with this building or you lose the building, because kind of trying to just keep it going is not going to allow you to have the true functions that you want, and it's going to cost you a lot of money just to throw energy and minor maintenance into over the years.
So in essence, what you're saying is that the building is in the condition that it's in and not worse because it has so little insulation.
Exactly.
If it had ever had insulation, then the juxtaposition of the heat and the cold would have made the brick crumble even more.
As Brandon was kind of demonstrating in that slide, if you were to insulate from the inside, instead of just having spalling on the exterior like we see, you'd start to have spalling on the interior of the wall. And then you have, and we've seen this, catastrophic failures of brick structures in kind of unexpected ways, particularly where you have floor beams connecting in, and then you have something break away and your whole floor is dry. Hence, hence my hesitation to push you in that direction. We have about 5 more minutes, I think, right, until the next town comes to visit us. But we're still open for any questions you might have.
Do you have a written report that we can look at when you're done?
So we're going to share the PDF of this presentation. What we've learned in the past is we used to deliver written reports, and they basically sat on shelves and nothing was ever done with them. So our new mode of operation is that we do these presentations and we share our PDFs. We could share our calculations, but these calculations aren't ones that you would act on, right? These are estimates that we use to come up with this report, with the hope that if you make a decision to move to another stage, we're available to help you take the next step, whatever that is.
And we'll share the recording of this presentation.
Right. Well, yes, Carol?
Thank you.
Thank you so much. Excellent,
Yes,
really.
this will give us a lot to discuss.
Yes.
Yeah.
Yeah, thank you guys very much. Thanks for inviting us
Thank
to the project.
Thank you
and-
for all your work.
And congratulations to Megan, Olivia, Mike, and Brandon. They put a lot of work in on the past semester.
Yeah,
I think we have to have some further discussion on this for sure, so. Oh, Lord, all right.
exciting though, it's exciting. Very,
MA.
very and exciting. And the next information we need is how on earth do we get money? You guys are good at that, right? Or should we go to the economics department?
We're not good at getting money. Lauren is good at finding some of the funding resources that are available, particularly from the state. But yeah, I think one place to look for money is if you are intending to, if you had in your budget to build town offices somewhere else, you had in your budget to build this auditorium, make a comparison between the upfront cost to build a new building versus the upfront cost to bring these buildings up to the status.
Right.
they need. And then essentially you're investing in the same thing, just in a different form.
Yep.
Well,
All right.
Thank you very much. We're going to stay on, and I suppose you're welcome to listen to the presentation for Long Meadow. They should be here in a few minutes.
I think I will depart. So thank you very much. Bye-bye.
Thank you.
Thank you very much.
Thank you. This was very interesting.
Thank you.
Bye-bye. Thank you.
Yeah.